As always in Maya, you need to have a project folder to manage your assets. Premium subscribers can download the exercise files. But if you don't have the exercise files, you'll need to create a project folder within Maya and then save files out as you go. To create a project folder, go into the File menu and go to the Project window. And you'll see my current project is the default one. It's in Current User Documents Maya Projects. To create a new project, I'll click New, and I'll just leave it at that same location, but I'll give it a new name. We'll call it Maya Bullet Project. And click Accept. And that has created the folder and also pointed or set Maya at that folder. So if we go to the File menu and choose Open Scene, it takes us to Documents Maya Projects, Maya Bullet Project, Scenes. But it's currently empty because we haven't saved anything in there yet. And we can see that here. If I minimize Maya and go over to Current User, Documents, Maya, Projects, here it is, Maya Bullet Project. That's the process if you don't have the exercise files. If you do have the exercise files, you can put them anywhere that's convenient. I put them on my desktop here. And if we open that up, we will see that there are a bunch of Maya ASCII scene files in the Scenes folder. Okay, so if you do have these files, then you'll want to set Maya to that project. Go back to Maya, go back into the File menu, but this time choose Set Project, and then navigate to wherever that project is located. Currently, it's in Aaron F. Ross Desktop. And just select the file folder and click Set. And now if we go into the File menu and choose Open Scene, it'll take us to the exercise file scenes, and there they all are. Okay, we're ready to begin dynamic simulations with Maya Bullet. If you open a Maya scene that includes some Bullet component, then Maya will know to automatically load the Bullet plugin. However, if you're starting from scratch, you'll need to load the plugin manually in order to get access to the Bullet menu up here. So let's enable the Bullet plugin. Go to the Window menu and choose Settings, Preferences, Plugin Manager. And you might need to scroll down a bit to find the Bullet plugin. You can turn it on by clicking Load, and as soon as you do that, you will see the menu appear. You can also enable Auto Load so that the next time you launch Maya, the Bullet plugin will load automatically. Up here at the top, you'll also see ABC Bullet. That's the Alembic plugin for Bullet, so that you can import and export Alembic cache files. And we might as well just turn Load and Auto Load on for that as well. And now, as you can see, once again, we have the Bullet menu available. As with all 3D computer graphics, before we begin, we need to establish a scale convention. In other words, are the objects in the Maya scene built at the same size as real-world objects, or are they a scale miniature? This is especially important with dynamics because if we don't get this right, then the dynamic simulation will not be physically accurate and we will have a lot of problems. For historical reasons, Maya expects that a dynamic scene will be built at 1/100th scale. So in other words, instead of having a character that's 2 meters tall, Maya dynamics assume that your character is 2 centimeters tall. And again, that's how you'll get best results with Bullet, is to build your scenes at 1/100th scale. However, with a simple scene like this dominoes setup, it's okay for us to model our scene at a unity or 1-to-1 scale. And in fact, that's what I have done here. Let's just walk through setting up the scale conventions in Maya. The first thing we need to do is just to check in on our current linear working units. That can be found under Window, Settings, Preferences, and in the Settings section we'll see Working Units Linear. They're currently set to centimeter. And in fact, I recommend that you leave it at centimeter. You can choose some other option here like meter or foot or whatever you like. That's not going to affect your scene. It's not going to affect the dynamics. It's just going to measure the world with a different yardstick. Again, I recommend that you leave it at centimeter. Go ahead and click Save. The grid is another consideration. How large is the grid and what is the spacing of the grid? To work with that, we'll go into Display, Grid, and go to the Options box. And these are the default grid settings for Maya. We have a grid that's 12 units from center to edge in the perspective view. And because our working units are centimeters, the grid is 12 centimeters from center to edge here. I want to make this more of a metric setup, so I'm going to set my length and width to be 150 centimeters. I'll define a grid line every 100 centimeters and 10 subdivisions per grid line. And that will give me a grid line every 100 centimeters and a subdivision line every 100 divided by 10, or subdivision line every 10 centimeters. And so that we can see the difference between grid lines and subdivision lines, I'll set the grid line to be a different color. We can click Apply, and now you will see that if we close the window and back out, we'll see that the grid is 150 centimeters from center to edge. And each one of these dominoes here is a few centimeters in height. If I select one of these, you'll see that it's very small relative to this 10 centimeter square. Once again, this scene is a one-to-one scale, and that's fine for a simple rigid body simulation in Bullet. If you're going to be working with soft bodies, then I recommend that you build your scenes at a 1/100th scale, and you'll just have a lot better results with Bullet. The default animation and playback ranges in Maya begin on frame 1, as you can see here. The Bullet simulation is also defaulted to begin on frame 1. However, this might result in some errors with the simulation as you rewind and play it. Just to ensure that you'll have better performance and fewer issues, I recommend that you set your playback and animation ranges to begin on frame 0, and that way you'll have a 1-frame run-up before the simulation begins. So I'll just simply go here and set the first frame of the playback range to frame 0, and that'll automatically set the animation range to frame 0 as well. And I'll give myself some more time here at the end too. I'll set the end of the playback range to frame 600. And I just set the playback range so that Bullet will perform more efficiently. When working with any form of animation, dynamics included, it's very important that we know how fast the timeline is playing back. Otherwise, when we render or export the animation, we may get an unpleasant surprise. It may play back faster or slower than what we saw in Maya. I've currently got 600 frames in my timeline, and when I press play, it only takes 2 or 3 seconds to play those 600 frames. My time base is currently the default 24 frames per second, and at that frame rate, it would take 25 seconds to play back 600 frames. So clearly, the Maya timeline is playing back faster than real-time speed. In order to verify this, we can enable the frame rate, go into Display, Heads-Up Display, Frame Rate, and then play the animation. You'll see that we're getting, in my case, almost 400 frames per second. To constrain that to real time, what we can do is right-click on the timeline and choose Playback Speed, Play Every Frame, Max Real Time. We do want to choose that option rather than the real-time option, because if we chose real-time, then Maya would skip frames in the timeline in order to maintain an overall frame rate. But if frames were skipped in the timeline, that would cause the dynamic simulation to break. Therefore, we need to choose Play Every Frame, Max Real Time. So in a heavy scene, the timeline will run more slowly, and in a lightweight scene, like this one, in which there's nothing happening, it will never exceed the current time base. Play that back and you'll see we're getting 24 frames per second now. With our scale and playback options established, now we're ready to begin creating our Bullet simulation. Let's start with this ground plane. It's not going to move during the simulation, and for that reason, it doesn't need to be fully dynamic. And we can make it a passive rigid body. Select the ground plane and go into the Bullet menu and choose Create Passive Rigid Body and go to the option box for that. Here we have two important properties. the collider shape type and the body type. The collider shape type is the shape of the object for purposes of collisions. So you can see that we could choose from these primitives, for example, plane. However, for best results, we would probably want to choose mesh because it's going to be the most accurate. But you'll see that it's grayed out here. The mesh collider shape type is only available for a specific type of body, and that's a static rigid body. So to access that, we'll need to go down into body type here and choose static. You'll also see kinematic and dynamic. Static bodies are ones whose collisions are only calculated on frame 1. So you cannot move a static body over the course of the animation. A kinematic rigid body's collision properties are calculated on each frame, and we could animate a kinematic rigid body with traditional keyframing, and it could push other objects around. And of course, a dynamic rigid body is one that fully participates in the simulation. It can push other objects and be pushed by other objects. In this case, once again, we want static body because it's a non-moving, passive rigid body. Once we've chosen static body, then we can go up to the collider shape type and choose mesh. And that's going to be the most accurate collision detection. Go ahead and click apply and close. As soon as we issue that command, we will see for the selected plane object, the translate and rotate channels are all highlighted in bright green. This indicates that there's a special type of incoming connection called a pair blend. And what it's doing is it's actually mixing the transforms from the traditional transform matrix, position, rotation, scale. It's mixing that with the dynamic simulation. So that's why those are turning green now. We can also take a look at the bullet solver. Go into the bullet menu and choose select solver. To see a more complete view of all those attributes, we could go to the attribute editor, hit Control-A on the keyboard, and here we've got the attribute editor. I'm going to actually tear that off so it's in its own floating window. And in the attribute editor, we can see solver properties such as acceleration, and scrolling down a little bit, we have some display options. We can also get to that solver by using the outliner. We go to Window Outliner, and scroll down at the bottom, you'll see Bullet Solver 1 is listed there. So if we select something in the outliner, then its attributes are displayed in the attribute editor. That's just another way of accessing those attributes. Let's make the dominoes dynamic. I'll close the attribute editor, and I want to select all the cubes. Probably the easiest way to do that is through the outliner. I'll select the last cube in the list and then scroll up to the top, hold down Shift and select the first cube. Now I've got them all selected, as you can see. And with all those cubes selected, go back into the bullet menu and choose Create Active Rigid Body and go into the options. And we'll see the collider shape type is box by default. And that's fine because in fact these are boxes. If we had a more complex shape, then we would want to choose hull. And a hull would actually be the convex shape of a particular object. Basically, the bullet solver is not smart enough to deal directly with concave surfaces like depressions and holes in objects. And so the hull is a simplified version of the mesh for the purposes of collisions. In this case, of course, once again, we can choose box because the dominoes are actually just boxes. And the body type we'll leave also at dynamic rigid body. Go ahead and click apply and close. And once again, all of those cubes now show their channels for translate and rotate in green, indicating that there's a pair blend node there. If we press play in our timeline now, we won't see much happening. We might see them move a little bit, but because there are no forces acting in the world currently, really we don't see much happening. If we try to play the simulation now, we might see some unexpected results. Basically what you have to do is let the simulation play through at least once for it to actually refresh. You get in very close here and rewind back to frame 1, and you'll see that they jump a little bit, they move up. And that's because the default collision radius is actually a bit high, and we probably want to reduce that. We can select all of the cubes once again, And in the channel box, scroll down to the very bottom and we will see collider shape margin. And it's currently set to 0.04 centimeters. Let's reduce that amount to 0.001 and press enter. And then rewind. And when we play back, we still see the same thing happening. And we also have to go into the plane and do the same thing there. 0.001 for the shape margin. And now when we rewind and play back, they don't move very much. Cool, so we've got basically initial condition for the dominoes. In order to set our dominoes in motion, we'll need to knock over the first domino. We could do that by pushing it with a kinematic rigid body. But there's an easier way. Just give it an initial velocity. And this is an unseen force that's built into the rigid body. Select that first domino and go over to the channel box and you'll see initial velocity x, y, and z. I do want to move the domino in the z-axis. You can see z down here is this axis. If I give it an initial velocity z of, let's say, 1, that will impart a force to that object pushing in z on frame 1 of the simulation. If we try to play the simulation now, we might see some unexpected results. Basically what you have to do is let the simulation play through at least once for it to actually refresh. I'll press play and you'll see that it does indeed fall over, but it's going in positive z and we need it to go in negative z. I'll set initial velocity z to -1. Press enter, rewind and play back the simulation. And you'll see that it does indeed work, but it seems like the dominoes are moving in slow motion. We are playing back at the correct speed, 24 frames per second here, but the objects are moving way too slowly. This is happening because, once again, the dynamics engines in Maya all assume that the world is built at 1/100th scale. But in this case, my dominoes are built at a 1-to-1 scale. Well, we will resolve this issue in the following movie. With our scene built at 1-to-1 scale, the objects move very, very slowly. And once again, that's because Bullet expects the scene to be built at 1/100th scale. We can work around this by increasing the strength of gravity, multiplying it by a factor of 100. Select the Bullet Solver node and go to the Attribute Editor, Control A, and you'll see under Basic Fields, Gravity. And it's got a Y value of -9.8. meaning that gravity is pulling down in the negative y-axis at 9.8 meters per second squared. To increase the strength by a factor of 100, we'll set the gravity to be a value of -980. And then when we rewind and play back, we'll see something kind of strange. The objects all fall through the floor. But we can work around that by a combination of things. First of all, we can adjust this internal fixed frame rate. Bullet actually is designed to work with real-time game engines and simulation engines. And so we have an internal frame rate for the Bullet system itself. And if we increase that frame rate, we will have more accurate calculations. Let's set that internal fixed frame rate to 240 Hertz or 240 frames per second. Rewind and play back. And you'll see that they don't fall through the floor, but they do act a little bit strange. And we can work around this as well. There's a clever feature of Bullet which allows us to make objects initially asleep, which means that they won't move until something hits them. I want to select all of the cubes except for the very first one. And with all those selected, go to the channel box. And you'll find there's an attribute near the bottom called Initially Sleeping. Select that and type in the value of 1 and press enter. And now Initially Sleeping is on for all of the selected dominoes, just not the first one. Rewind and play back, and you'll see they don't do anything because nothing has hit them. We see that that first domino just wiggles a little bit. The initial velocity isn't strong enough to overcome this very strong gravity. What we can do is just select that first domino, go back up to the top, and you'll see we've set an initial velocity z of -1. Let's try a value of -50 or so, and then play back. Rewind and play back. And you'll see now it gets knocked over really quickly. Maybe negative 50 is too much. Let's try negative 30 or 20 or something like that. But just fine-tune that until it feels right. Cool, so now we've got the basics of our simulation working. In this chapter, we'll look at keyframing in combination with dynamics. And the first thing I want to show you is how to resolve an issue here. When I press play, you will see that although the dominoes all fall over just fine, after they're supposed to have settled down, they're still kind of moving around and maybe even jumping up and down a bit. The reason this is happening is because we have a very high gravity of 980. That was necessary for this particular scene because it was modeled at 1-to-1 scale. And this does highlight some of the issues that you may encounter when modeling objects that are not at a 1/100th scale. However, we can resolve this. All we have to do is keyframe the gravity in the bullet solver node. I'll play it back until all of the dominoes have fallen, and here around frame 70 or so, I'll select the bullet solver node in the outliner and keyframe the gravity. Select gravity Y, and then in the channels menu choose channels key selected. And we've got a keyframe here now in the timeline. And just advance a few frames and set the gravity back down to negative 9.8. Negative 9.8. Select the name of that channel once again, go to channels key selected. And after that point, we don't see the objects jumping around so much. So I'll rewind and play back the entire simulation, and we'll see that we've got a good result here. We can actually help this a little bit more. You'll notice that this first domino is still kind of sliding around a bit. That's simply because we've got a pretty high initial velocity. I'll select that first domino, go back up to its initial velocity z, and maybe set that down a bit to, let's say, negative 10. Rewind and play back the simulation. And we got a pretty good result here now. We can even clean this up a little bit more, but to do that we'll need to bake the simulation. We'll see that in the next movie. Once the bullet simulation is approximately good, we want to convert it to keyframes. And that way we can actually... Once the bullet simulation is approximately good, we want to convert it to keyframes. And that way we can actually render this shot without having any issues of long render times or perhaps the simulation going haywire during the render. To bake to keyframes, what we'll want to do is select all the moving objects. So back in the outliner, I'll select all of the cubes, holding down Shift and just making sure those are all selected. And I also want to select the translate and rotate channels in the channel box. Just click and drag the mouse across translate and rotate. And then go up into the menus and choose Edit, Keys, Bake Simulation Options. Click on that option box. In the Bake Simulation Options dialog, we just want to choose under Channels from Channel Box. That means that keyframes will only be created on the selected channels. And you'll see time range is set to time slider. That means it's going to generate keyframes for the entire timeline here. We don't actually really need that because we only really have about 150 frames of animation. I'm going to choose a start and end time here. I'll say start time of 0 and an end time of 150. And click Bake. And the simulation will play through. And when it's finished, you'll see that we have keyframes in this entire region here for the selected objects. So if I select any one of these, you will see that we've got keyframes for position and rotation. And we can actually scrub across here. But we still do have bullet nodes attached to all of these objects. And just to clean this up, we'll want to delete those bullet nodes. Once again, select all of the cubes. Go up into the bullet menu and choose Bullet. Remove Bullet from Selection. We're not actually deleting the bullet solver node, but we could if we chose Delete Entire Bullet System. In this case, I'm just going to opt to remove bullet from the selected objects. And now you'll notice that all of the rigid body nodes, so the bullet rigid body nodes have disappeared here. Okay, now we can actually scrub through without having any issues whatsoever. At this point, we could actually render our shot, but there's still a little bit of cleanup that we could do to make it better. After about frame 75 or so, there should be no motion. So we want to delete all the keyframes for these dominoes after that point in time. I'll select all the cubes in the outliner, and in the timeline here, hold down Shift and drag across to select all these keyframes up to about frame 75 or so, and then right click and choose Delete. Now after frame 75 there should be no motion. You can rewind and play that back. Okay, and just so that we can see this a little bit better, I'm going to set the end of my animation range to 100 frames. We can clean it up a little bit more as well because these are still moving around a bit. After about frame 25, we probably don't want this second half of dominoes to move. So I'll drag a selection rectangle around all of these, and then once again hold down Shift and use a left mouse button and drag across in the timeline to select all of those keyframes. Right click and choose Delete. Rewind and play back the animation. We could even make this better by simplifying. You can go into the graph editor and simplify these curves. With those dominoes still selected, go into Window, Animation Editors, Graph Editor, and press the F key to frame all the curves for the selected objects. And we can drag a selection rectangle around those and simplify these curves. And that way we could edit these if we needed to. Go to the Curves menu and choose Simplify Curve Options. And importantly, we want to change the time tolerance. Let's set that down to a lower value because it's not accurate enough, and a value of 0.05 seconds will have some artifacting with our animation. So we need to bring that down to 0.01 and click Simplify. And now we've reduced the amount of data here. Go ahead and rewind and play this back. Okay, now if we need to, we can go back in and just hand keyframe some of these. I could select a few of these, go back into the graph editor that I had minimized, and we can even, delete some of these keyframes here. Just delete those and sort of clean up the animation completely. Okay, so we could actually go back into the graph editor and fine-tune this even more, but at this point we've essentially got the result we need. We've got the basic rigid body simulation with Bullet. Now we'll take a look at how we can combine traditional keyframed animation with Bullet dynamics. In this case, we'll set this ball in motion with keyframes and then have the Bullet solver take over. We'll begin by selecting that polygon sphere and going up into the Bullet menu. And we want to start by creating a passive rigid body. Go into the options for that. And we want to choose Sphere as the collider shape type, because it's a sphere, and our body type will be kinematic rigid body. And once again, a kinematic rigid body is one that can be animated with keyframes, and it can push dynamic rigid bodies around. Click Apply and Close, and then create some keyframes. On frame 1, I'll keyframe Translate Z. Select Translate Z, the name, and choose Channels key selected. I'll go forward a little bit to, let's say, frame 6, and then grab the Move tool and move that ball forward a little bit. And then once again, with Translate Z selected, choose Channels key selected. You can rewind and play that back to verify that we've got some animation there. And just to make sure that we don't have any issues, we want to make this a linear interpolation. With the ball still selected, go into Window, Animation Editors, Graph Editor, and if you need to, press the F key to frame that curve, and then select all the keys and set it to linear tangents, and that way the ball will be at a constant rate of speed. It's not going to do an ease in on frame 6. Okay, very good. So we've got those keyframes created, and in the next movie we'll look at actually keying the type of rigid body from kinematic to dynamic. At this point we've created our hand animation. We've got just 6 frames of animation on that ball, and we want the bullet solver to take over so that the ball will continue to move under the force of gravity. I'll select the ball, go over to the channel box, scroll down, and we're looking for the body type, and it's currently set to kinematic. Select the name, body type, and choose channels, key selected, and then go down to frame 6, the same frame at which we have our final keyframe, and change the body type over to dynamic. And then select the name, body type, and once again choose channels, key selected. Rewind and play it back, and we can see that in fact the bullet solver takes over. All we need to do now is to select the ground plane and choose bullet, create passive rigid body options. The body type will make static, and the collider shape type mesh. Click apply and close, and now we've got a dynamic simulation that started from a hand keyframed animation. Our simulation is looking pretty good, but it would look better if we had a little bit of bounce on that ball. So let's add bounce. In Bullet, bounce is known as restitution, and it needs to be added to both of the colliding objects. I'll select the ball and the ground plane and go over to the channel box and scroll down, and you'll see friction and restitution. Friction is set to its maximum of 1 by default. Restitution is bounce, and with a restitution of 0 we get no bounce. If we set restitution to its maximum of 1 for both the ball and the ground plane, then we would get some strange results. Press play and you'll see the ball bounces up very high. And if I dolly back a little bit here, we can see that really clearly. That's not a realistic result. The ball is not obeying the laws of physics. There's no way it could bounce up higher than its initial position. What we'll do is just reduce that restitution to a lower value of, let's say, 0.8. Rewind and play back. And now we're getting a much better result. I'll dolly forward a little bit and rewind and play this back once again, and you may notice the ball going through the floor on certain frames. If I step through one frame at a time, we'll see that at that point of impact the ball is actually going through the floor. Now you might think that you can fix this by setting a different value to the collider shape margin here, but in fact the real issue is that the solver is not accurate enough for these fast moving objects. we need to change the solver's time base or temporal resolution. Let's select the solver, going into the bullet menu and choose Select Solver. And once again in the channel box, we'll see internal fixed frame rate. Let's set that to 120 Hertz or 120 frames per second. Rewind and play back, and we no longer see the ball going through the floor. You will notice that that did change the simulation, and we're getting a different result now. And in fact, the ball is having a little bit of spin on it, and that's because we have such a high friction value. I can select the ball and the ground plane once again, going back into the channel box and bring that friction down to, let's say, 0.1, and play the simulation back. And now the ball is actually moving farther on that one bounce because there's less friction. Let's try a value of 0.5. And we're actually getting a pretty good naturalistic result. And that's how to fine-tune the bounce and restitution attributes for the bullet solver. And that concludes our second chapter in integrating keyframes with dynamics. In this chapter, we'll examine bullet rigid body constraints. In this chapter, we'll examine bullet rigid body constraints, and that's a way of limiting the movement of rigid bodies. For example, the hinge of a door. I'm going to use this ball, throw it against the door, and knock it open. To begin, let's open up the outliner so that we can see all the objects in the scene listed. Window outliner. I want to select the ground plane in the outliner and go up to the bullet menu and choose Create Passive Rigid Body and go into the options. The body type should be static and the collider shape type mesh. And click Apply and Close. Now the ground plane has been made a static body and the bullet solver node has been created. Next I'll select the ball, go back up to the bullet menu and choose Create Active Rigid Body options. The shape type should be sphere because it's a spherical object, and the body type dynamic. Click Apply and Close. I'll dolly back a little bit here and press the play button and we'll see that ball fall to the ground. And it's falling at the correct speed because I've built the scene at 1/100th scale. Rewind back to frame 0. I'll select the door now and make that into an active body as well. You'll notice that the door has a couple of children. These doorknobs are children of the door. And although the door will be dynamic, the doorknobs are not. They will just follow the door because they're children. Select the door and go up to the bullet menu and choose Create Active Rigid Body options. The shape type should be box this time. And click Apply and Close. Once again, rewind and play the simulation to see what we get. And both the ball and the door fall over. Now we've got all the elements in place, we're ready to create the constraint. Once again, with the door selected, go back into the bullet menu and choose Create Rigid Body Constraint options. And there are several different types of constraints listed here. There's only one constraint node, but it will behave differently depending upon which option you choose here. And really the only difference is which axes are allowed to have freedom. So for a hinge constraint, only the z-axis rotation is permitted, and all the position axes are locked, and the x and y rotations are also locked. Go ahead and click Apply and Close. And if I tumble around, you'll see that at the origin we now have an object, and that's actually the rigid body constraint node. We can select in the outliner here as well. If we try to play the simulation now, we might see some unexpected results. The door still falls over. We would expect that it would not fall over, but basically what you have to do is let the simulation play through at least once for it to actually refresh the simulation. So I played it through a few times. You can see the door is not falling any longer because its position transforms are now locked according to the constraint. In the following movie, we will look at positioning and orienting the constraint so that we will get a proper hinge on the door. Now we're ready to move the constraint to the edge of the door in order to make the door hinge properly. I'll select the rigid body constraint and grab the Move tool. And so that we can see this more clearly, I'll press the 4 key on the keyboard so that we switch to wireframe mode. If I just move the constraint upward, we will see something strange. The constraint actually moves to the side. And if I move it forward, we will see that it doesn't really track with the transform manipulator, or the Move tool. Don't panic, this is just a little bit of a minor display glitch. If you simply rewind in the timeline, that will refresh the simulation and the constraint will snap to the position of the Move tool. Alright, let's go into the top view, tap the space bar, go over to the top view, tap the space bar again, and I just want to position that constraint over on the edge of the door, dolly forward a bit. Once again, remembering that the constraint won't refresh until we rewind. So I'm going to position this right on that corner of the door, right here, and then rewind and we will see that constraint node snap to the position of the Move tool. Tap the space bar, go back out again, tap the space bar over the perspective view, and we also need to rotate that constraint. Grab the Rotate tool, and we want to snap rotate, so hold down the J key on the keyboard and rotate around the x-axis 90 degrees. And now we've got that rotated. So essentially that's in position now. And we can go ahead and move on to the next stage, which is to send the ball moving towards the door. Select the ball and give it some initial velocity in z. Let's give it an initial velocity z of -10. Press enter and press play. Now you'll see that the door is actually moving, going according to that hinge. When we play back the simulation, we will see that the door sort of stops, as if there were some limit on the constraint, but we haven't imposed any limits yet. The reason this is happening is because the default friction is 1, and that friction actually applies to the constraints. To work around this, what we'll do is just select the door and go into the channel box and give it a friction of 0. Rewind and play that back, and now you'll see that door swings around pretty much endlessly. We can also play with the bounce factor, which is restitution. Let's select the door, the ball, and the ground plane, and give them all a restitution or bounce of 0.5. Rewind and play that back. Now we have a little bit more interesting result. The other thing we want to look at is the mass of the objects. And if the ball, for example, has a high mass relative to the door, then the door will get pushed more by the ball. I'll select the ball and scroll in the channel box looking for mass. And I can increase that. Let's give it a value of 10. Rewind and play back. Now you'll see that the ball pushes a lot harder against that door and it continues onward. Whereas if the ball had a mass of only 1, then the impact with the door would slow the ball down a lot more. Likewise, if we played around with the mass of the door, we would get different effects. If I go to the door and increase its mass, let's say give it a mass of 50, rewind and play back, we'll see that the ball actually bounced off. We did see, once again, a little bit of a display glitch there the first time the simulation played, where it looked like the ball's mesh and the ball's rigid body nodes separated. If you see that, don't panic. Once again, just allow the simulation to play all the way through to the end of the timeline, and the second time it plays through, it should be fine. Okay, the effect that I really want is for that ball to push all the way through into the house, so I'll set the door's mass back down to 1 and give the ball a mass of 10. Rewind and test that. Okay, we've got our restitution, friction, and mass all set properly. At this point, our hinge constraint is working, but it has no limits, and so the door is able to spin around endlessly. Let's apply some limits to the rotations of that constraint. Select the constraint node, and note that the rotate X value for that constraint is negative 90 degrees rather than positive. Let's open up the attribute editor, Control A, and in that constraint shape node, open up limits, and you will see angular constraint Z is set to free, and we want to choose limited. And now with angular constraint minimum and maximum in Z both set to 0, there will be no rotations, so it's not able to actually rotate. Let's set the angular constraint maximum in Z to a value of 160 degrees. And now if we get in close on that constraint icon, we can see that it actually shows us the range of rotations here. If I set this to a lower value like 90 degrees, we would see that there's less of a rotational freedom. Set that back up to 160. And now if we play our simulation, the door actually only is able to rotate 160 degrees. Once again, remember that you may need to play the simulation through more than once in order for it to sort of refresh and play back properly. Having set limits on the constraint, now we're ready to fine-tune the simulation. If you look closely when you play back, you may see that the door jumps a little bit on frame 1. And that's once again due to the collision shape margin. Let's select the door, the ball, and the ground plane. Go over to the channel box and scroll down to the very bottom and set the collider shape margin to 0.001. And then when we rewind and play back, we won't see the object jump like that. Remember that you may need to let the simulation play through completely from beginning to end once in order to fully update the simulation. Okay, now we can control the amount of bounce back from the constraint, and the way to do that is to go into the constraint node and the attribute editor, Control A, and in the limit properties you will see angular limit softness, limit bias, and limit relaxation. And these control the amount of bounce. Angular limit softness is actually kind of paradoxical because as you increase this value, you're reducing the amount of softness. And softness is kind of difficult to see, actually. You may actually adjust this value and really not see it do much, but what it's supposed to do is sort of ease into the limit and then ease out as it comes back. So if you have a value of 1, that means there's no softness, that it's completely hard and there's no ease in, ease out. And that's actually what I want in this case. Then we come to the limit bias and the limit relaxation. And these both control the amount of bounce. And they're a bit cryptic as far as what exactly they do, but we will see that if we reduce both of these down to 0 and rewind and play the simulation, we may need to let it play through more than once. we do that, then we will see that the door actually just comes to a dead stop when it hits that limit. For best results, we probably want to have a low limit bias and a low angular limit relaxation in this case. And that way we'll just get a little bit of bounce back. If we want more, of course, we can increase these two attributes. Let it play through all the way once again. Another thing that you may notice is that the door will come to a sudden stop after it sort of moves around a little bit. It may actually just kind of come to a dead stop like that. And we can prevent that from happening by making sure that the door never goes to sleep. When an object goes to sleep, it's because its velocity has gone below a certain threshold. And we can't really adjust that threshold, but we can tell the object to never go to sleep. So I'll select the door, go to its rigid body shape node, and enable the switch that says never sleeps. Rewind that and play it back. And we can see that it doesn't come to a dead stop like that. Finally, we can also adjust the accuracy of the simulation by going into the bullet solver node and playing around with the internal fixed frame rate. Maybe increase that up to 120 Hertz. You can even crank it all the way up to 240 Hertz. Having done that now, we don't have any artifacting with the door actually moving when it hits that limit. Cool, and if we want to, we can actually select the door and give it a little bit of friction. Just a tiny amount of friction, maybe 0.1. That'll be a little bit more naturalistic. Okay, that's how we can fine-tune limit properties, and that concludes our chapter on rigid body constraints. This chapter is all about rigid sets. A rigid set is a collection of rigid bodies that are all treated as one. And this excels at simulations when you have many objects that need to collide. And in this example, we will break a glass into shards. To begin with, we have to have an unbroken object and we have to generate a broken object. And to do that, we will use the Maya shatter effect. To prepare for that, we need to delete the construction history on our objects. I'll select both this glass and the ground plane. Go up into the menus and choose Edit, Delete by Type, History. And now there's no longer any history on those objects. We get in a little bit closer on that glass object by selecting it and pressing the F key on the keyboard. It's a good idea to position and rotate the object first before you run the shatter effect. So I'll go ahead and just rotate this a little bit so that it's not square to the world. And to access the shatter effect, we need to go into the Dynamics menu set. Choose Dynamics from the menu sets. And under Effects, go to Create Shatter Options. And you'll see that there are three tabs here: Surface, Solid, and Crack. The one we want is Solid Shatter. Increase the shard count here. Let's just turn that all the way up to 10 and give it a little bit of edge jagginess. We don't want to change the materials. I've got a glass material on this object, so I want to disable the option to apply the interior material. And we also, just for convenience, we can hide the original object. With all those options chosen, we can go ahead and click Create. It'll take a second to calculate. Be aware that the shatter effect sometimes will crash, and you may need to run it more than once. Maybe just change some of those parameters and run it again. But in this case, I had no problems. And so you can see now we've got a bunch of shards. They've all been placed into a group. You can take a look at that. Go to the window outliner, and you'll see Solid Shatter 1 is the group name. And there are a bunch of shards inside that. With our shard effect finished, we'll now create the bullet simulation. First, we need to make the ground plane a collision object. So select that ground plane and go into the bullet menu and choose Create Passive Rigid Body Options. The body type should be static, and the collider shape type will make mesh. And while we're here, let's reduce the collider shape margin. My scene is built at 1/100th scale, and the collider shape margin value of 0.04 equates to 4 centimeters in the 1/100th scale world. We want to reduce that down to a millimeter, 0.001, and click Apply and Close. And now let's create the rigid set for these shards. Select all the shards, go into the bullet menu and choose Create Rigid Set Options. And let's give it a more descriptive name. I'll call it Shards Rigid Set. And click Apply and Close. Once we do that, we will see some new things appear in the outliner. We see Shards Rigid Set, and that's a set that includes all of our shard objects. And we'll also see Shards Rigid Set Solved, and that's the end result. There are also a couple other nodes that we don't see, and the most important one is the initial state node. And this is a shape node that is now attached to the bullet solver. And we can see that if we go into the outliner and choose Display Shapes and open up the bullet solver, and we will see a bunch of stuff in here, including the initial state. And that's where all the dynamic properties for the rigid set are going to be found. We can select that, and now we will see these attributes appear in the channel box. There's another way that we can get at that as well. If we select the rigid set here in the outliner, and even if we don't have the shapes visible, if we select that set, we can go into the bullet menus and choose Bullet Rigid Sets, Select Initial State. And once again, that's going to select that initial state node, which contains all the important attributes. Most importantly right now is the collision shape margin. Because all these shards are actually touching one another, we want to set the collision shape margin down to 0 so that they won't explode on the first frame of the simulation. I'll set that shape margin down to a value of 0. You'll see there are also other attributes in here like damping and friction and restitution. We'll leave those for now. Let's back out here, dolly back a little bit, and play the simulation, and we'll see all the shards fall through the floor, and that's just because the solver has got a low temporal resolution. So we'll go to the bullet solver and go into that shape node for the bullet solver and change the internal fixed frame rate to 240 frames. Rewind and play back. And you'll see that the shards are all still sort of exploding, but we will fix this in the next movie using glue. At this point we do have a rigid set, but it looks like it's still exploding. We need to hold all those parts together. Let's go ahead and select the rigid set initial state node once again. There's yet another way to get at it. We can select the bullet solver and go to the attribute editor, Control A, and from here we can select the initial state tab. We can get at the attributes from here. What we want to play around with are the collision attributes here. Specifically, the first thing we need to do is change the shape type from box to hull. And once we do that, we should see a better result, because even though we had set the collision shape margin down to 0, if the collision type is box, then they're still overlapping, and that causes them to explode away from one another. Okay, now the next thing we want to do is give it some glue and hold the parts together. And we will find that in the initial conditions section here. So initial conditions, you'll see glue shapes, and we can turn glue shapes on. Rewind and play back, and you'll see it's now holding together. Very cool. Well, we don't want it to hold together forever, of course. We want it to hold together until it hits the floor, and then all the parts break apart. So we can keyframe the glue breaking threshold attribute here. I'll go to frame 0 and set the glue breaking threshold to a high value of 100, and then right click and set that keyframe there. We'll step forward one frame at a time in the timeline. And just to make sure that we're keying on the correct frame, let's look at this in the orthographic view. So I'll tap the space bar and go over to this side view. Press the F key to frame that selected object. And we want to keyframe the glue breaking threshold just one frame before the impact. Going forward, it looks like it's going to hit the floor on frame 14, as we can see here. On frame 14, I'll set the glue breaking threshold to 0, press enter, right click, and set key. We've created two keyframes for the glue breaking threshold, but what we need to do is go into the graph editor, because currently the breaking threshold is actually interpolating. It's reducing the amount over time, and what we want is just a sudden cutoff. So what we'll do is we'll go ahead and make sure that we have the rigid set initial state node selected, and then go into the graph editor, window, animation editors, graph editor. Press the F key to frame that, and then select these keys and make them step tangents here. And that way there's no interpolation. We'll have maximum glue until frame 14, and then it'll just jump down to 0 amount. Alright. Cool, so we can play that back. And that's exactly what we want. We can maximize our perspective view once again. Rewind. Cool. We make this a little bit better just by putting some restitution on the ground plane. Select that ground plane, go into its rigid body shape node, and I'll set the friction and restitution here both to 0.5. Rewind and play back. Now I've got a little bit more interesting result there. Our trick of animating the glue is working well for holding these parts together. However, if we rendered it this way, we would actually see the cracks between the different shards. And to prevent that, we would actually want to render the original object in the period of time in which it was falling, and then render the shards or the rigid set after the point of impact. To make that happen, we should probably make the original object a dynamic object too, so that it falls at the same rate. I'll select that original glass object and make it visible once again by typing in a 1 and turn it into a bullet object. Go to the bullet menu and choose Create Active Rigid Body Options, and the collider shape type should be cylinder in this case, and the body type dynamic, and the collider shape margin once again 0.001 or 1 millimeter. Click Apply and Close, and now that's been made into a dynamic object. However, if we play this back, what will happen is it actually collides with the rigid set on the first frame of the simulation, and so we're getting a very weird result here. The result that we want to see is the two of them fall together exactly in sync. The first thing we want to do is to place the original object on a different collision filter. And a collision filter is basically a layer. And we can say certain objects will not collide with other objects depending upon which filter they're in. With that glass original object selected, I'll go to the attribute editor, Control A, and scroll down a bit in collision filters. And what we're looking for here is default filter. We want to uncheck that. It's no longer in the default filter. And if we play this now, we will see that it doesn't collide with the rigid set. It's still allowed to collide with the ground plane, but not the rigid set in this case. Cool, so that solved that little issue. There's one other little minor thing we would want to look at, which is that they're not falling at exactly the same rate of speed. We can see that in the orthographic view. I'll tap the space bar, go over to the orthographic view, and step forward one frame at a time, and we can see that the original object is falling a little bit faster, and the rigid set is falling a little bit more slowly. You can get in really close on that around frame 13, and we can see that pretty clearly. The reason this is happening is because the rigid set has some damping on it, and the original object does not. So let's select the rigid set and go into the bullet menu so we can select the rigid set's initial state node and bring its damping values down to 0. Rewind and play back, and they fall a little bit more precisely together in sync. Cool. So then the last thing we want to do with that is to keyframe the visibility, and we'll do that in the following movie. To substitute the objects, we'll keyframe their visibility. We want the glass mesh original to be visible before the impact, and we want the shards rigid set solved to be visible after the impact. On frame 0, I'll select glass mesh original and key its visibility on. Select visibility and choose channels, key selected. And the shards rigid set solved, set the visibility to 0 or off. Select the name and choose channels, key selected. And then we'll just go down one frame at a time until frame 15 in this case is when I want that transition to happen. And on frame 15, with shards rigid set solved still selected, I'll turn visibility on. Now don't be alarmed by the way that you can still see it even though it says visibility off. If we rendered this right now, it wouldn't show up. There's just no way for us to actually hide it in the viewport, but it won't be visible for the purposes of rendering. So I'll go ahead and set this to visibility of 1 or on, select the name and then key selected, and then go back to glass mesh original and make it invisible. We might not even really need to do this because in fact it's gone through the floor, but just to be on the safe side, I'll go ahead and key it. And it's not visible after frame 15. And we can verify that in fact by selecting glass mesh original, and it's highlighted in green. Play the simulation and we don't see it go through the floor. It disappears on frame 15. The breakage simulation is looking okay, but I'd like to see those shards settle down a little bit more quickly. They are just a bit more overactive than I'd like. We can accomplish that through damping. I'll select the shards rigid set and go back into the bullet menu to choose rigid sets, select initial state, and we will see here in the channel box we've got linear damping and angular damping. We just want to keyframe those values to increase the amount of damping over time. Rewind and play this back. I'll start the damping on around frame 40 or so. So I'll step forward one frame at a time. Around frame 40, I'll keyframe linear and angular damping. Linear damping is positional and angular damping is rotational. Having selected both of those, I'll choose channels, key selected, and I'll go forward about a second to about frame 60 or 64 or something like that, and increase the linear and angular damping amounts. The maximum is 1, and if I set it to 1, they would kind of come to an unnatural dead stop. So instead of a value of 1, I'm going to put in a value of 0.99 for both linear and angular damping, then select their names and choose channels, key selected. Rewind and play that back. And the parts have sort of settled down a little bit more gracefully. They don't wiggle around quite as much. We could also go into the graph editor if we want and play around with that. Just go to Window, Animation Editors, Graph Editor, and we'll see linear and angular damping. Press the F key to frame that, and it's probably going to work better if these are just linear. So I'll change those over to linear tangents. Okay, so now we've got a good simulation. As with all Maya dynamics, we need to bake or cache the simulation before we can render it. If we don't do this, then we may have some serious issues, such as the rendering coming out wrong. The simulation may be different during the rendering. Or we may have extremely long render times because each frame takes longer and longer to calculate because the simulation has to run up to the current frame that's rendering. To avoid those issues, we can bake to keyframes. We're going to use two different processes for that. For the rigid body, which is the original object here, the unbroken glass, we'll just use a standard bake simulation. For the shards, we're going to use Alembic, which is an open source file format developed at Industrial Light and Magic, and it's sort of a Swiss Army knife for importing and exporting data between various programs. Before we begin, we should save our scene out to a new file name so that we don't have any problems of potentially overwriting the existing data. So let's do that first. I'll do a file save scene as command. And this one's called 0407 Alembic, and I'm going to put at the end of that Alembic baked and save as. Okay, that's been saved out. Next, let's open up the outliner and get at our original object, glass mesh original, and we're going to bake the simulation for that. Go to Edit, Keys, Bake Simulation Options, and we only want to key the channel box Selected Channels, and we want to only key from frame 0 to 15. We don't need to bother creating anything else because the object's going to disappear after frame 15. Select the Translate and Rotate channels by dragging the mouse across them and click Bake. So now that one's been baked out, and that's fine. Now we need to export to Alembic. To do this, we need to select in the outliner the rigid set node. We can't select the solved or anything else. It has to be the rigid set node that includes all of those shards. With that set node selected, go into the bullet menu, choose Bullet, Export Simulation, Export Selection to Alembic. And the first thing you need to know is that this process will fail if you try to save out to a path that has a white space in it. And unfortunately, that is the case I have here. My current user is Aaron F. Ross with white spaces in it. And I actually cannot save out to this folder. Normally, this is what you would do. You would save into the current project cache Alembic. But again, because this has white spaces in it, it's going to throw an error. So what I'm going to have to do is actually type in temporary folder here. I've got a folder called temp on my C drive, and then press the enter key, and that's now taken. And I want to change some options over here. The time range is going to be the time slider. Scrolling down through all of this stuff, we want to make sure that strip namespaces is on. And finally, the file format has to be HDF5 and not Ogawa, which is the default. Okay, so with all those things set, we got to give it a name, and I'll call it Shards Cache, and it'll have the extension .abc appended to the end of it. And click Export Selection. Now that's been saved out, and the next thing we need to do is to move that ABC file from the temporary directory, because again, in my case, I have white spaces, so I couldn't save out into the project directly. In your case, you may have been able to save out to your project folder directly, and if that's the case, then you won't need to do anything here. But I'm going to have to move the file, minimize Maya. Here's my temporary folder. I want to select this file and copy it, right-click and copy. And it needs to go into the current project cache Alembic. And I'll right-click and paste into there. Okay, so now I can go back to Maya. The next thing I need to do is to copy the visibility keys that I created previously. You'll see here, shards rigid set solved. We previously created keyframes for the visibility there. And I want to copy those keyframes over onto the existing objects that are going to receive this animation. So our original solid shatter objects are the ones that are actually going to render at the end of the day. So I'm going to take the visibility keys from this rigid set, select visibility, go to channels, copy selected, and then go over to the solid shatter 1 group node, and then with visibility selected, choose channels, paste selected. So I've pasted those keyframes in. And also I need to unhide the shards themselves. Open this up and you'll see all the shards are actually hidden. Drag my mouse across all of those and set their visibility to on or 1. Press enter. Now when we re-import the animation from the Alembic file, the shards will be visible at the times that we want them to be, because their visibility will be controlled by the keyframes on this group node here. Okay, so with all of that done, now we can delete the bullet system because we've exported everything and we're ready to re-import it. Go up to the bullet menu and choose delete entire bullet system. Next we need to import the animation back onto the solid shatter node. So select that group node, go up into the menus and choose pipeline cache, Alembic cache, import Alembic. And it'll take me directly to the exercise files or current project cache Alembic. Select it and make sure that you choose import under current selection and merge. Those are not the default options. The default is import to scene root. We need to choose import under current selection and merge with that group node selected. And click import. And now if we play back, it works perfectly. We actually have the animation applied onto the shards, each one individually. And if we investigate this, we can actually see the link to the Alembic file. If I select any one of these shards, you'll see in the inputs here that there is an Alembic node. And if we go to the attribute editor, Control A, and go to that Alembic node, you'll see that there's a link to cache Alembic shardscache.abc. Okay, so that is a link that needs to be preserved. We can't ever move, delete, or rename that, or else our animation will go away and we'll get no result here. So that can't ever change. That's going to be in your project forever. Okay, very good. So with all of that done, now finally we can resave the file. Remember, the file that's currently open is the one that's labeled baked. So we can just now save again. And now this shot is completely ready to render. In fact, I've already got a camera here. If we go to Panels Perspective, Camera 1, this is now ready to render. Okay, cool. So that's how we use Alembic to bake the simulation for a rigid set. I know that was a little bit of a convoluted process, but that's what you have to do with Bullet in order to make sure that your rigid set will play back exactly the same way every time, and that your renders will behave as you expect them to. And one last note is that you can actually use this process to take keyframes from a proxy set of geometry and apply it onto a higher level of detail set of geometry. As long as they're all named the same and are under the same hierarchy, you can actually use this to export the animation out of Bullet and then import it into another scene that has a higher level of detail. Alright, cool. So that's our whole workflow for rigid sets in Bullet. Our final chapter in this course is all about soft body dynamics in Bullet. And soft bodies can be used for creating cloth simulations and things like inflated balls and other objects that need to deform. The soft body solver in Bullet is a basic one, and it's not a replacement for Maya's more advanced nucleus N-cloth simulator. And if you want to do fancy simulations, for example with cloth draped over characters and things like that, then you will want to use N-cloth, and I recommend you check out my course here at lynda.com entitled Understanding Maya N-cloth. Okay, so let's take a look at Bullet soft bodies. I've got a simple piece of drapery here that's been built at 1/100th scale, and that is very important for soft bodies in Bullet. If your scene is built at some other scale, then basically soft bodies in Bullet will not work. So it's kind of a hard requirement that your scene be built at 1/100th scale if you want to do a cloth simulation in Bullet. Okay, so just select that piece of drapery and go into the Bullet menu and choose Create Soft Body Options. And within here, very importantly, we want to enable Generate Bend Constraints so that we will actually have links between the vertices on the polygon mesh, and we'll actually be able to prevent things like incredible stretching and so on. And we also probably want to turn on self-collision so that the cloth will not be able to self-intersect. There's some more attributes in here. We're going to take a look at some of those a little bit later. But basically, we've got the essentials here. Go ahead and click Apply and Close. And if we rewind and play this back, we will see the cloth fall. Now, if we want to get a better sense of this, we can enable an implicit ground plane in Bullet. And to do that, we'll select the Bullet Solver. Bullet, select Solver, and go into the Attribute Editor, Control A, and you will see here Ground Plane. And that's going to be positioned at a Y value of 0, so right on the XZ plane. Try to play that back, and you can see now that we've got a cloth simulation. Now you do notice that it looks a little bit odd and dancing around quite a lot, and that's mostly due to the fact that we've got a pretty high collision margin. So I can select the object and go into its soft body shape node, and we're looking for the collision margin. That's going to be under Soft Body Solver Collision Margin, and it's currently set at 1 centimeter. I'll bring that down to 1 millimeter, 0.001. Rewind and play that back, and now you'll see that we don't have that strange result of it sort of like jumping before it falls to the ground. Additionally, you'll see position iterations here, and that's the quality of the Soft Body Solver for that particular object. And the value of 10 is kind of a low value, so I'm going to increase that a little bit to a value of 20. That's going to increase the quality. And finally, I can also go back to the Bullet Solver node, Bullet Select Solver, and set the internal fixed frame rate up to its maximum of 240 Hertz. And you see that's running a lot more slowly. So let's split the difference here. We'll set it to 120 Hertz, so we'll have more or less real-time playback in our viewports. To constrain the drapery so that it doesn't fall to the floor, we can use soft body anchors. And an anchor can really be any object that has a pivot point. I'm going to choose to use a locator because that's a simple way of creating an anchor that won't render. Go to the Create menu and choose Create Locator. And we want to reduce the size of it, but it's not a good idea to use the scale attributes here. It's just a better practice to use the icon size whenever possible. With that locator selected, I'll hit Control A to open up the attribute editor and reduce the local scale in X, Y, and Z down to 0.05, pressing the Tab key to go to the different fields. And now that locator is small enough that it's not going to be intrusive in our scene. Grab the Move tool and position it so that it's sort of in the fold of the cloth there, and then move it up in the front view till it's sort of hovering over the drapery a little bit. Next, we need to select a vertex. Let's get in real close in here. We want to select that drapery object and then right click and choose Vertex Component Mode. Select that nearby vertex and then hold down Shift and drag a rectangle around the locator to select it. With that component vertex selected and the locator selected, we can go into the Bullet menu and choose Create Soft Body Anchor. And we get this anchor icon, and it's kind of large as well. we can select that anchor object and reduce the icon size here to, let's say, 0.03. Alright, let's test this. Tap the space bar, go out to a full frame view here in the perspective view, and play it back. And we'll see that it is in fact anchoring, but it's not anchoring absolutely in place. You can see that there are some dots here. That's a spring that's connecting the locator to the anchor. We can control the strength of the anchor, but we can also add more anchors. So let's do that. We'll add a few more anchors here. Rewind, tap the space bar, and go back out to the top view and select that locator and make a duplicate. Just use the keyboard shortcut, which is Control D, to make a duplicate. And then drag that new locator over. Now we've got two of them. And then select both of them and hit Control D again. We can duplicate two at a time here. Hit Control D yet again, and I've got two more. And we need a total of 7, so let's select this last locator here and hit Control D, and now I've got that last locator. So we've got a total of 7 locators. And we just want to repeat the process by selecting a vertex and then selecting a locator and making a new anchor. Right click, go into vertex component mode, select the vertex, shift select the locator, and choose bullet, create soft body anchor. And then reduce the icon size to 0.03. And repeat that for the rest of these. Okay, I've created the rest of the anchors and I've expanded out the perspective view. Let's press play and see what we get. So they're holding on, but they could be holding on a little bit better. So in the following movie we will control that. The anchors are working, but they're still not quite holding the cloth exactly in place. There's a bit of a gap there between the locator and the anchor. We can fix this by just adjusting one attribute on the cloth. So we'll rewind, select the cloth, and go into its soft body shape node. And you might need to scroll down a little bit and you'll see anchor contact hardness. That is the strength of all of the anchors that are attached to this soft body. Increase that up to its maximum of 1. And then rewind and play the simulation, and now you'll see that it's holding in place just fine. Let's also adjust a couple other attributes in this shape node. Most importantly is the bend resistance. With a value of 0, we'll get a very shear effect to the cloth. If we want it to look thicker, then we'll increase the bend resistance a little bit. Let's set it to a value of 0.1. Rewind and play back. And now you'll see we're not getting as many folds and wrinkles in the cloth. It's acting more like burlap or some sort of thick canvas. Another thing I want to adjust here is the friction. It's set to a very low value of 0.01. And I want to increase that just a little bit. Set that to a value of 0.1 and play the simulation. And what that's going to do is cause it to resist movement as it touches that invisible ground plane. We'll increase it up even more, set it to its maximum of 1 so we can see the effect there. So with a friction of 1, it doesn't dance around as much on the invisible floor there. The value I really want is just 0.1. And once we've set all of those things, I think now we can turn the ground plane off. I'll select the bullet solver node and in the channel box go down to ground plane and set that to a value of 0 or off. And then rewind and play back. And now we've got a pretty good result for that cloth. And now we can add some wind to blow it around a little bit. Let's add some wind in order to get this drapery moving. Wind is found in the bullet solver node, but it only affects soft bodies. So wind will not affect rigid bodies or rigid sets. The best way to play around with something like wind is to use interactive playback. And that way we can let the timeline play while we adjust attributes and sort of feel our way through and find the right result. We need a lot of time in our timeline in order to really effectively do that. Down here I will set the end of my playback range to 10,000 frames. Now let's open up the properties and attributes for the cloth and also for the solver. Select the object and go to the attribute editor, Control A, and go to the bullet soft body shape node and copy the tab off to its own window. Drag that over. And we want to open up the aerodynamics section because these are important attributes here. In the attribute editor itself, we can open up the properties for the bullet solver. So go up to the bullet menu and choose Select Solver. And under Basic Fields, you'll see wind magnitude and wind direction. Now we're ready to enter interactive playback mode. Go back up to the bullet menu and choose interactive playback. I'll set the wind direction to -Z. So in the Z field here, we'll set that to a value of -1 and give it a little bit of wind magnitude. We don't need much in this case. I'll set it to a value of 3. We do have wind blowing in the scene, but it will not affect the cloth unless we have a non-zero value to drag and lift. And in order to give us a sort of really good feeling cloth, we want to have a little bit less damping here. So I'll set the damping down to 0.01. And then give it a little bit of lift. And as soon as we increase the lift, we'll see the wind is affecting the cloth. I'll set the lift to a value of about 4. And then we also have drag. And that should be a value in this case of, let's say, about 0.5. And we could increase or decrease these and see what it does. Interactive playback lets us do that. Pretty cool. So I think the drag of 0.5 and the lift of about 4 is a pretty optimal solution here. Alright, that's how you adjust wind for the soft bodies in Bullet. Once we're happy with our simulation, we'll need to export it to an Alembic file so that it can be rendered. It wouldn't be a good idea to try to render this Bullet simulation directly, because it won't necessarily play back the same way at render time. We might have some issues such as really long render times. We looked at exporting to Alembic using rigid sets, and that was a bit more of a convoluted, complicated workflow. Exporting a soft body is actually quite simple. The first thing we need to do is to identify what frame range we want, and I'm going to say I want from frames 200 to 400. And then just select the object and go up to the Pipeline Cache menu and choose Alembic Cache, Export Selection to Alembic. And we want to give it a start and end range here, say from frame 200 to 400. And only those frames will actually get saved out. Scroll down a little bit. We'll turn strip namespaces on just to be on the safe side. There aren't any namespaces in this particular scene, but we just want to make sure that they're removed. And the file format, we can choose HDF5. And let's give it a name. And we'll call it Drapery. And the .abc extension will be added automatically. And click Export. And that frame range will play through. Once that's finished, we can import into a fresh scene. We could re-import it into this same scene, but then we would have 2 copies of the drapery. And then go over to the Pipeline Cache menu and choose Alembic Cache, Import Alembic. And choose that drapery file and import it into the scene root and click Import. And now we've got our drapery. We'll need to change our timeline range here. We'll set it to 400 frames at the end. And the first 200 frames, there's no data. But then after frame 200, you will see we've got our drapery. And if we want, we can shift that so it will start on frame 1. We can select the drapery and then go into its attributes, Control A. And we've got an Alembic node here. And we can set an offset here. We can just set this offset value to -200 and then rewind. And you'll see the animation starts on frame 1. Alright, cool. The Alembic file, once again, is necessary. Our animation is actually being stored in this .abc file. And the scene file that I currently have open is actually just sort of a container for that. But if I want to, I can of course save this out. So I'm going to do File, Save Scene As. and we'll call it Alembic Soft Body Finished. Alright, we've got our simulation just the way that we want it, and we shouldn't experience any issues if we try to render this. The last feature we will look at in this course is pressure, which is a way of inflating a soft body so that we can, for example, make a ball bounce. A precondition of this is that you have a good structure to the soft body, and ideally all the polygons should be the same size. And I couldn't really achieve that with Maya tools because a standard sphere is going to have poles at the top and bottom. And you could try using an icosahedron and smoothing it, but once again, the polygons will not all be the same size and they will have strange poles on them. What I did end up doing is using the 3ds Max geosphere primitive. Take a look at that. I'll select that ball and press the F key. Tumble around so you can see that all the polygons are the same size. And that's just for best results so that the object will deform evenly. Okay, let's make the ground plane a passive collision object. Select that ground plane, go into the bullet menu and choose Create Passive Rigid Body Options. And we want to make the body type static, but very importantly, the collider shape type cannot be mesh as we have done previously, because currently soft bodies cannot collide with a mesh. It has to be hull or some other collision object type. Okay, click Apply and Close. And now we want to create a soft body on the sphere. Select it. Go back into the bullet menu. Create Soft Body Options. And in here we do want to enable Generate Bend Constraints, but we don't want to enable Self-Collision because this sphere's polygons are never going to collide with each other. And if we did turn on Self-Collision, we would get some strange results. Click Apply and Close. Don't be alarmed by this odd sphere here. That's actually the icon for the soft body. And we can't really do much about that. It's just going to hang out there in our scene. So don't be alarmed by that. Rewind, play back the simulation, and the ball acts like a piece of cloth. It just crumples. Let's adjust some of the important attributes. Select the ground plane, and we want to change its collision shape margin. So collider shape margin, we'll bring that down to a millimeter, 0.001. We also want to go into the solver node and increase its resolution. Bullet, select solver, and increase the internal fixed frame rate up to 240 Hertz. And now for the soft body properties. Go and select that sphere. Let's open up the attribute editor. Go to the soft body shape node. And let's increase the friction up to 1 and reduce the damping down to 0. If we have a non-zero damping amount, then the object won't really fall at the right rate and it won't really bounce very well. Also, we do want to have a maximum friction here so that the ball will actually sort of stay put after it bounces. It won't kind of swivel around and glide on the surface of the tabletop here. Okay, scrolling down a little bit, in soft body solver, we've got a collision margin of 0.01, and that default is actually going to work well for us in this case, so we're going to leave that alone. If we rewind and play this now, we still won't see any result, but if we open up aerodynamics, we can increase the pressure. Let's set that pressure to a value of 5. Rewind and play back, and now you see the ball bounces. Getting real close on that. Rewind and play it back. Pretty cool. Now we can control this by adjusting the amount of pressure. If we have less pressure, like a pressure of 1 for example, then the ball is not going to bounce as much, and it's as if it's been kind of deflated. The other factor that does control how much it bounces and how much it deforms is the bend resistance. Since we do have generate bend constraints enabled, then this bend resistance attribute is going to be effective. It essentially is the squishiness. So with a value of 0, we get a very squishy ball. Increase it all the way up to its maximum of 1, and the ball doesn't deform very much. We can maybe split the difference, set it to a value of about 0.5 or so. The important thing to keep in mind with pressure is that your soft body object has to be closed. It can't have any gaps or holes in it. And ideally, all the polygons should be the same size. Awesome. Well, that's a fitting conclusion for our chapter on soft bodies. And it also wraps up our entire course in dynamic simulations with Maya Bullet. This short course covered the major features of Maya Bullet, but there's always more to learn and experience. What you'll find with Bullet is that its value as a production tool only increases as you pile on more complexity. It's a massive improvement over the old school classic rigid body and soft body solvers in Maya. If you've got a solid video card with at least 1 GB of memory, then try enabling OpenCL acceleration in the Bullet solver node. You may find that it allows you to simulate ever more complex scenes with hundreds or even thousands of rigid bodies. That's something we could never do before in Maya, so it's really exciting. I hope you've enjoyed the course, and thanks for watching. Goodbye.